Hi, welcome to another video. So in this video, we're going to discover how to determine if a rational function has a horizontal asymptote. That's about it. The next video, we'll study oblique or slant asymptotes. Then we'll talk about end behavior. We'll just kind of practice finding all the asymptotes and holes of a function. And then we're going to put this thing all together in a graph. It'll be the longest video in this series. So in this video, when we talk about a horizontal asymptote, it's very similar to a vertical asymptote that we discovered. Vertical asymptote is like a force field, and you cannot touch it with the function. It will not touch. Horizontal asymptotes are not, of course, vertical, they're horizontal, and there are some different qualities. So here's how to determine if or when you have a horizontal asymptote of a rational function. So here's what we're going to do. We're going to look at our function, and we're going to look at the rational part as a polynomial over a polynomial. That's what defines a rational function anyhow. We're going to look at the leading term of the numerator and the leading term of the denominator. If you remember, the leading term is the term of the largest exponent in a polynomial. So basically, you want your rational function in order, both polynomials in order. And then we take a look at basically the first two terms, and we look at the degree. Remember, the degree is the power of your leading term of a polynomial. If the degree of the denominator, the bottom of your function, is larger than the degree of the numerator, you are going to have a horizontal asymptote at 0. Y equals 0, just like this, right on the x-axis, no matter what. If the degree of the denominator equals the degree of the numerator, you're going to have a horizontal asymptote at whatever the leading coefficients say, whatever the ratio is. We're going to practice that. Now, this is a really easy way to remember what to do. As we go through it, I'm going to explain why this actually works, because a lot of times students get this, they try to memorize it, they get it all screwed up. So I'm going to explain to you why this is the way it is. So we're going to be looking at degree of denominator, degree of numerator. Those are both polynomials. We're going to consider the two cases that we can have for greater than or equal to. So a horizontal asymptote will exist if the degree of the denominator is greater than or equal to the degree of the numerator. We're just kind of determining which is which. If the degree of the denominator is bigger than the numerator, then you're going to have a horizontal asymptote at y equals 0. If the degree of the denominator is equal to the degree of the numerator, we're going to have a horizontal asymptote at y equals the leading coefficients. So that's basically what I intend for you to learn in this video. Learn that what we're doing is putting polynomials in order on numerator, denominator, looking at the degrees. So the first terms, your leading terms, basically just saying, hey, end behavior is determined by leading terms. That's our second note right here. And then looking at the degree and saying, all right, what's going on here? If the degree of the denominator is bigger than or equal to the numerator, you're going to have a horizontal asymptote. We're just defining which one it is. If the bottom degree, the denominator degree, is larger than the numerator, it's going to be at 0 on the x-axis. Y equals 0 on the x-axis. If it's equal, so if the degree of the denominator equals the degree of the numerator, you're going to have it at whatever the leading coefficients say. We'll use that ratio. We'll talk about y. We'll talk about limits a little bit. The two notes I really need you to know, I mentioned this just a minute ago. We'll do number 2 first. End behavior is always determined by leading terms. Well, that's true for rational functions as well, except that on a rational function, you have two polynomials, one on the numerator and one on the denominator. So you basically have two leading terms, and that determines the end behavior of rational functions as well. As we move on, this video really could be a lot longer if I included every possible end behavior, but I'm breaking it up. I'm breaking up these videos as horizontal asymptotes, oblique or slant asymptotes, and then this end behavior where those don't exist. That is all types of end behavior functions. A horizontal asymptote is an end behavior. So as you go to the end of your function, what's happening? Is it tending to one y value? Well, that would be a horizontal asymptote. As we go to the ends of our function, are we tending to be along a diagonal line? Well, that would be an oblique or a slant asymptote. Or as we go to the ends of our function, are we tending to be like a parabola or maybe a cubic? Well, that's also end behavior. It's all one idea. We're just kind of categorizing two specific types. So here's what I want in your head right now. I want that End behavior or rational functions can be basically one of three things. Number one, you could have a horizontal asymptote in either of these cases. Number two, you could have a slant asymptote. That's a diagonal. If the degree of the numerator is 1 larger than the denominator, that's what's going to happen. Or you could have it where you don't have that case, where the degree of the numerator is larger than the degree of the denominator. In that case, you're just going to get straight up end behavior, like a cubic or a quadratic. They're all end behaviors, but you fall in one of those three cases. Let me make this very clear. You will never have both a horizontal asymptote and a slant asymptote. It can't happen. It's either horizontal or slant or neither, and you have some other end behavior. So keep that in your head for the next few videos. So let's go back to this. End behavior is always determined by leading terms. I'm going to fill this one out in just a second. Well, let's look at f of x. F of x is 4x cubed minus 7x plus 1 over 7x to the fifth plus 2x cubed minus 3. The leading terms are the terms with the biggest power, so the largest exponent in a polynomial. If you put them in order, they're always first. So when we look at our leading terms, leading term of the numerator is 4x cubed, and leading term of the denominator is 7x to the fifth. Now here's what we learned. We learned that end behavior is basically modeled by that. Well, for this bottom polynomial, it's basically modeled by that. So for our function itself, our function's end behavior is going to look approximately like 4x to the third over 7x to the fifth. Now, I want you to think about this for a second. If you just think about this and do this, it's going to work. This is a nice shortcut on how to determine, number one, if you're going to have a horizontal asymptote, and number two, which type it's going to be. So we can do that really quick. We can literally go, hey, okay, the degree of the numerator is 3. The degree of the denominator is 5. So let's go through it. Is the degree of the denominator greater than or equal to the degree of the numerator? Yes, it is. This is 5. That is bigger than or equal to 3. Okay, very good. Now classify it. So number one, we know we're going to have a horizontal asymptote. Now classify it. Is the degree of the denominator strictly greater than numerator, or are they equal? Let's see. 5 is not equal to 3, so we know that the denominator is larger than the numerator as far as its degree. So 5 is bigger than 3. What that says is that we are going to have a horizontal asymptote at y equals 0. So along the x-axis, as we go to infinities, and that's kind of a weird concept, it's called a limit. As x gets closer to negative infinity and positive infinity, this graph is going to get to 0. Either, let's see, probably like this, because it's like a 1 over x squared, probably like this. This is going to tend to be really, really, really close to 0 as we go to infinity. That's what's going to happen. So we're going to identify that right now. We're going to say, all right, there is a horizontal asymptote at y equals 0 on both sides. So as we get to positive infinity and negative infinity on the x-axis, this graph is going to approach the x-axis. Y equals 0 is the x-axis. It's getting really close to that. Now we're going to graph that as we move forward. We're going to see what that looks like. But in our head, we know that's going to happen. Now I want to show you why. So that's kind of a shortcut on how you do it. You go, oh yeah, look at the degree, great. Is it bigger than? Cool, y equals 0. Is it equal? All right, y equals the leading coefficients. We'll talk about that. Now, why is that? Well, if you think about end behavior as being the leading terms, notice what you can do. Here we took a leading term of 4x cubed over 7x to the fifth. We said, yeah, our end behavior is going to look about like that. Well, let's simplify that. If we simplify that right now, we would simplify and get x to the second power. That's 4 over 7x squared. And then we do a little bit of imagining. You think critically. You think, if this is how our function is going to behave as we get really, really big and really, really small on the x-axis, so really positive and really negative, this is how it's going to behave. It's going to follow this for sure, positively. And we can simplify it to make it even easier to think about. Now, the reason why we simplify, it's really difficult to think about x getting very large in both a numerator and a denominator when they both have variables. That's very difficult. So with our leading terms, really focus here, with our leading terms, we should always be able to simplify so that either our numerator or our denominator x's disappear. That is always the case. Now here's why that's the case. We have leading terms which are always power functions. Power functions always have one variable raised to an exponent. If we have one of those on the numerator and one of those on the denominator and you're in the same variable, you can always simplify them. So taking your rational function and your leading terms of both polynomials, putting them in a ratio, you can always simplify them. So do it and then think about it. This is much easier to think about. Think about what's going to happen when you really think. Stop, do not fast forward this video, really think about this. When you take x and make it very, very large positively, or I know it's kind of oxymoronical, but very, very large negatively. Think about that. What's going to happen to the 4? If I start taking x and putting in really big values for x, what's going to happen to the 4? Nothing. The 4 is going to stay the same. What's going to happen to 7x squared as x gets close to like 1 billion, 1 trillion, like way more than that? Well, close to infinity is what we'd say, positive infinity. 4 divided by a number that's enormous, like really, really large. 4 divided by 1 billion, I mean, that's already really small. Imagine this. Imagine taking $4 and dividing it amongst 1 billion people. Are those people going to get a lot of money? No. They're going to get hardly nothing. They'll get basically nothing. You don't even have a monetary value for that. We don't even have stuff that small, okay? Now, 1 billion's not even close to infinity. Not even remotely close. So take 4 and divide it by 1 billion billions. What's that value going to get close to? Not equal. That's not what limits are about. Limits are about what's your function getting close to. As x gets to this value, close to it, what's your function getting close to? Well, as x gets close to infinity, this function is getting really close to 0. Oh, that makes sense. As x gets close to positive infinity, our function gets close to 0. As x gets really, really, really big, man, if you understand this, limits in calculus are going to be a breeze. As x gets really, really, really big, this gets bigger and bigger and bigger. 4 stays the same. That's why we simplified it, so you could see that. 4 stays the same, this gets huge. 4 divided by huge is close to 0. It's not 0, it will never equal 0. It's never going to intersect that x-axis. It can't. I hope you listen to that. It can't ever equal 0. 4 divided by huge numbers are never actually equal to 0, but getting so close that you couldn't even slip a piece of paper in between them. Like it's that close. This is going to what we call approach 0. It's going to get super close so as to tell no difference, but there is a difference. So as x approaches positive infinity, our function is approaching 0. It's never going to equal there, but it's approaching. That's what the arrow signifies. It's this word approaching. What about negative infinity? As x approaches negative infinity, does that do the same thing? Well, let's think about it. 4 would stay the same. Remember that. That's why we simplify, so you can see that 4 acts as a constant here, and this denominator is what is growing larger and larger. That's why we get the 0. So the denominator grows larger and larger. Imagine negative infinity. Plug in like negative 1 billion, okay? Then square it. Oh, that's positive 1 billion. 4 divided by 7 times a positive billion squared, or whatever that is, that's also really close to 0. So as x approaches negative infinity, we're taking and squaring that number, aren't we? So let's see, 4 divided by another huge positive number, it's going to be close to 0. In calculus, we go a little bit further. We define these as limits. We talk about taking the limit as x approaches positive and negative infinity, seeing what the signs do. This will also tell you in which way your function is approaching 0. Is it approaching 0 positively? Is it approaching 0 negatively? In this case, we're approaching 0 positively on both of these cases. But we talk about that a little bit later when we start getting into graphing. You really won't even need it the way I'm going to teach you, but in calculus, it's kind of important to know. So this is the basis behind why in the world we get a horizontal asymptote at y equals 0. I know I'm going very deep into this, and I know that most textbooks just go, just do this. Yes, but when you get to calculus, you're going to want to know why this is. This is the why. When you take a leading term divided by a leading term, you can always simplify it. That simplified leading term, the ratio of leading terms, is going to tell you your end behavior. So all we're really doing is we're saying, okay, what's happening as x is getting really big and really big positively and negatively. We use that sort of terminology. What's happening when x is getting really positively big or really negatively big? Well, that's called end behavior. That's at the end of our graph. In this case, 4 stays the same. This gets enormous. 4 divided by enormous is close to 0, approaching 0. That's the idea of an asymptote. It gets really close, but does not ever touch it. That's what we're doing. That's why this is here. Hopefully you can see it now. Hope you can see that, well, yeah, every time the degree of the denominator is bigger than the numerator, what am I going to get? I'm going to get constant over variable. That's what I'm going to get. If the degree of the denominator is larger than the numerator, then I will always be able to simplify this power function. It will always give me a constant over a variable if the degree of the denominator is larger than the numerator. That needs to make sense to you. Try even change it if you want to. If we change this to a 4, well, then I would just get x to the first power. Does this still hold true? Yes, it does. It approaches 0 more slowly, but 4 would stay the same. X would get really large. 4 divided by really large is close to 0. As x gets really large positively, the function gets close to 0. A constant divided by something approaching infinity is going to get close to 0. Like this. Now, what about as x approaches negative infinity? 4 divided by 7 times something really out there large negatively, that's still going to be close to 0. 4 divided by like negative a trillion or something, or negative 7 trillion, whatever you want to say. 4 divided by that is super close to 0, but it's approaching it negatively. So this graph looks like positive close to 0 and negative close to 0. It's sort of doing two different things. Oh my gosh, that seems like an odd vertical asymptote kind of flipped on its side. Wait a second, that's odd. What? Same stuff. Do you remember this one? Like 5 seconds ago? I said it probably looks like this. Why? Because that looks like 1 over x squared or something very similar to it. The end behavior is modeled by that. That's why we're studying this stuff, because it's really quite interesting that happens. So back to here, this will also still approach 0. You'll still have a horizontal asymptote at y equals 0, for sure, without a doubt. So I hope that makes sense. I hope that you understand that we're taking leading terms, we're simplifying, and we're just thinking. We're just using our critical thinking hats and saying, what's happening as x is getting big, positively, or big negatively? Are we getting close to 0? Are we getting close to a number? And it will bear out. And if you understand your end behavior, it's going to bear out. It's going to actually be modeled a lot by the reciprocal function, this 1 over x sort of thing, or the 1 over x squared a lot of the times, or reflected if you have negatives. In fact, I want to talk about that right now. What if this were a negative? Would that change this? No, it would not. So negative 4 divided by something really large is still close to 0. No matter whether you have positive or negative, this is still going to be a horizontal asymptote at y equals 0. Now, your graph will change, of course. It will be reflected. So think about this. Man, I hope that you're thinking with me here. If I took x to positive infinity, just plug in something huge. Negative 4 divided by something really big positively is going to be close to 0, but it is going to be negative. A negative divided by a positive. Even if it's a huge number, it's close to 0, but it is negative. This is going to go to a horizontal asymptote this way, from the negative side of the x-axis. Remember, this is the x-axis. Y equals 0 is the x, so we're getting there from the negative side. Now divide a negative by something getting really big negatively, like negative 7 trillion. Negative 4 divided by negative 7 trillion, negative divided by negative is a positive. It's still close to 0, but it's going to get there from the positive side of the x-axis. If that makes sense, you are going to be a rock star when we get to graphing rational functions and we need to calculus, because we do the same exact thing. And that idea of a limit, that's one of the fundamental concepts in Calculus 1, is just getting your head wrapped around what a limit is. That's it. A limit means, what is the function doing? What's the value of the function approaching as we get closer and closer and closer to some x value? That's basically what it means. All right, the other thing that I need you to know is that Because end behavior is as x gets really large and really small, we actually can cross a horizontal asymptote. We can do all sorts of stuff between a limited number of x values, but as we get closer to infinity, that stops happening and then our end behavior takes over. So this is different than a vertical asymptote. I need you to really get this. In a vertical asymptote, that value is completely undefined. You can never touch it. It's like MC Hammer. Do. Can't touch this. Like, never. But a horizontal asymptote is different. You can cross a horizontal asymptote. Horizontal asymptotes take kind of effect after you get outside of a certain range of values. And I can't tell you exactly what that's going to be. It just happens as x is approaching positive and negative infinity. So think way out there. So keep this in mind. You can cross a horizontal asymptote. That is absolutely possible. I will show you an example where that happens. Kind of difficult to deal with, actually, but I will show you that. You can't cross a vertical, you can cross a horizontal. All right, let's get on to our last example here. So we got g of x equals 8x to the third minus 2x plus 3 all over 2x cubed plus x squared minus 7x plus 5. And we're just talking about horizontal asymptotes right now. We're not even talking about vertical. We're not talking about x-intercepts. Just whether or not we're dealing with a horizontal asymptote. And here's the class it falls in. A horizontal asymptote falls into a class of what is called end behavior. What's happening is the function is going left and right forever. So positive infinity and negative infinity, we talked about it in polynomials. We knew that odd was like this and even was like this. We're going to deal with quite the same thing, only now we have these other two. We have like a 1 over x, it's going to look like this. 1 over x squared is going to look like this, or reflected. 1 over x squared. We can, 1 over x cubed would look a little different than that. So we can have those things as far as end behavior. It's just going to bear that out a little bit. So what we do here is we take a look at our leading terms. So when we look at our leading terms of polynomials, in this case we have 8x to the third and 2x to the third. Those are our leading terms respectively, just the first two, because they should be in order. Now, if we want to come over here, let's make sure this actually works. So are we going to have a horizontal asymptote here? Well, all we've got to do is really look at our degree. So the degrees are 3 on the numerator and 3 on the denominator, just right there. And those happen to be the same. So we think through it. Is the degree of the denominator greater than or equal to the degree of the numerator? Yes. Yes, it is. They're actually equal, but yes, they're greater than or equal. And so we know right now that we are going to have a horizontal asymptote for sure. That is going to be the case. Now, let's qualify what type that is. Are we going to have a horizontal asymptote at y equals 0? Well, that only happens if the degree of the denominator is strictly bigger than the numerator, and it's not. They're equal. Okay, they're equal. What's that mean? Degree of the denominator equals degree of the numerator. Then we're going to have a horizontal asymptote at y equals, and this might be a little confusing, but the fraction of leading coefficients. Wait a second, the leading coefficients come from the leading terms. Okay, so let's walk through our end behavior. Our end behavior says g of x should look a lot like that. It should be modeled by that at the ends of the functions. It'll appear to be this. The leading coefficients are just the numbers in front of your leading term. So like 8 and 2. So what this says, it says, hey, look, the degree of the denominator and numerator are the same. You have equal degrees. You are going to have a horizontal asymptote, but it's not going to be at 0. That only happens when the degree of the denominator is larger than the numerator. In this case, you just go, all right, well, what's going to happen here? Well, our horizontal asymptote is going to happen at y equals, just take your leading coefficients, make them a fraction, and simplify. That means we would take 8 over 2. So at y equals 4, remember that y equals 4 is a constant, a horizontal line, just like this. So at y equals 4, 8 divided by 2 is 4. We are going to get this horizontal line, and your function will approach that. It'll never equal it at infinities. Maybe it'll cross it, sure. But as x approaches positive infinity, and as x approaches negative infinity, this function will approach. It'll get really close to the value of y equals 4. The function's value will be really close to 4. For sure. Now, let's study why that happens, because I want you to really get this. So if n behavior is determined by leading terms, and we have two leading terms, one from the numerator and denominator, we can make a ratio. Hey, we've done that. Let's simplify that. You go, well, wait, if these are power functions, all of the variables can simplify, right? Same thing here. We can simplify power functions very easily. In this case, though, if your degrees are equal, what is going to happen to your variables? If your degrees are equal, you're going to cancel them out. They're going to be completely gone. If your degree of your denominator is larger here, you're going to get constant over variable. Variables can grow, constants can't. That's why this one went to 0, because the constant stayed the same as the variable was growing. That's why it happens. That's why if the degree of the denominator is larger, you're always going to get y equals 0 for your horizontal asymptote. But wait, if your degrees are the same, they're going to all cancel out. Do you see it? Do you see, like, if I have a 3 over 3, x to the third over x to the third, it's going to cancel. Or x to the fifth over x to the fifth. Or x to the degree over same degree. This is always going to cancel out and give me a constant. And what that says is that g of x is going to be about 4. That's the end behavior for it. Well, what's that mean? If that's a constant value, that means that you have a horizontal asymptote of that value. It's not 0 because there's nothing to grow larger than the numerator here. You're basically saying as x approaches positive and negative infinity, they're approaching at the same sort of rate and the coefficients take over here. So we go, all right, well, what happens as we go to x positive infinity? Well, you're going to get close to 4. How about negative infinity? You're still going to get close to 4. What we do end up losing a little bit is what direction we approach it. We'll need some more math to do that. It's not like this one where you still have an x, you go, okay, I can kind of deal with signs here. Well, that's positive, but it's not telling you what direction you're approaching that horizontal asymptote. All we know in this case is that we have a horizontal asymptote at y equals 4. That's pretty much it as far as how to determine whether you have a horizontal asymptote. And we're going to deal with this throughout the next 5 videos, is when we have a horizontal and when we don't. When you have a horizontal asymptote, and it's actually quite easy to do. I overtalk this because I want you to understand it. I hope you get that. I'm not just getting you to do it. I want you to fully grasp what is going on. I'm trying to tell you limits. So as x approaches positive infinity, if you want to write this, as x approaches positive infinity, g of x approaches 4. As x approaches negative infinity, g of x still approaches 4. It is a constant. It can't change. That's why we have that just horizontal asymptote at 4, because it can't change. It's going to be there. The function is going to approach that. So I want you to get that. I want you to understand that really the basics are, look at your degree, just compare them. If the degree of the denominator is bigger than the numerator, you have a horizontal asymptote at 0. If they are equal, you have a horizontal asymptote at the coefficients of your leading terms. That's it. Now you probably should have a question, right? You should have a question, what happens if the degree of the numerator is larger than the denominator? Well, we have 2 more cases, and that's the next 2 videos. The next video is, what if the degree of the numerator is larger by 1? Well, then we have, well, wait a minute, what would happen? Think about it. What would happen? If the degree of the numerator is larger by 1, you take n behavior, just like this, and just like this, but you'd simplify. What would happen if you get, I'm just making this up, a numerator larger by 1? Well, your power function would still simplify, and you would get 4x. Well, what's 4x? Wait a minute. 4x looks a lot like slope-intercept form. The slope is 4x to the first power would be a diagonal line. That's called an oblique asymptote. That's what we're going to study in the next video. What if the degree of the numerator is larger by more than 1? So what if it's like x to the 6th? Well, then you get x squared. And you know what your end behavior is going to look like? A parabola. That's all there is to it. We're just making end behavior. Where it gets a little complicated is these are 2 end behaviors you haven't seen before, where we have a horizontal asymptote at 0, horizontal asymptote at a constant. That's basically it. So I'll come back with another video about oblique or slant asymptotes, they're sometimes called, and then we'll continue.